Okay guys, in this next video we are going to start reaction stoichiometry. So there's going to be a lot of numerical problems in this one. And so we'll be using chemical equations to derive amounts of both reactants and products. And we'll be doing calculations involving moles and mass and also molarity. So this diagram essentially explains what a stoichiometric calculation is. And the heart of any stoichiometric problem involves a mole to mole conversion using the stoichiometric coefficients in the chemical reaction. So the chemical reaction itself can be used as a conversion factor between reactants and products, or between reactants and reactants, or between products and reactants. Okay, and that conversion factor works on the mole level. So moles of species A here to moles of species B, using these coefficients to convert from one to the other. Okay, so that's the heart of any stoichiometric problem. Now, not every problem is going to give you moles of reactant. Oftentimes they're going to give you the grams of reactant, and they're going to want to ask how many grams of this product can you make from this many grams of reactant. And so there we have to tack on additional conversions. You would take the mass in grams of your reactant, convert that to moles using the molar mass, and then you would convert from moles of your reactant to moles of your product using the stoichiometric coefficients, and then you would use the molar mass of your product to convert the moles of product to the mass of product in grams. Okay, and so that's a very common stoichiometric problem, a gram to gram conversion. If you're dealing with, let's say, an aqueous solution, you might be given the volume of a particular solution and the molarity of that solution. Well, then you can use the volume and the molarity to calculate the number of moles of your reactant. Then you use the stoichiometric coefficients to calculate the moles of your product, and then you may need to use the molarity of the product to calculate the volume of the product. So that would be a volume to volume type of conversion. You could also do if you knew density rather than molarity, you could do the conversion that way. It's a little silly to go from number of particles to number of particles, but in principle you could do that using Avogadro's number as the conversion factor. Okay, so there's and you don't necessarily have to go from mass to mass. You could go from mass to number of particles, or from number of particles to mass. So any of these boxes here on the left-hand side can be connected to any of the boxes on the right-hand side through these different conversion factors. And that's what we're going to practice in this video. So it's just going to be a whole bunch of problems at this point. So here we've got a chemical reaction, nitrogen reacting with hydrogen to yield ammonia, and we're just going to do some mole-to-mole conversions using the stoichiometric coefficients. So how many moles of ammonia can be produced from 2.4 moles of nitrogen? Well, we've got 2.4 moles of nitrogen, and we are going to use the stoichiometric coefficients to convert from nitrogen to ammonia. Now we want the nitrogen to cancel out, so we're going to put 1 mole of ammonia on the bottom. 1 mole of nitrogen on the bottom. I'm using 1 mole because the stoichiometric coefficient is 1 for nitrogen. The stoichiometric coefficient for ammonia is 2, so I'll have 2 moles of NH3 in the numerator. And so I simply need to double this number. You see that the moles of nitrogen cancel out, and we'll be left with moles of ammonia. In part B, how many moles of hydrogen are required to produce 15 moles of ammonia? So here we have a desired amount of product. Well, how much of this reactant do we need? So in part B, we've got 15 moles of NH3. This time we want the NH3 to cancel, so we put the 2 moles of NH3 in the denominator. And the stoichiometric coefficient for hydrogen is 3. So we're going to have 3 moles of H2 in the numerator. So we'll take 15 times 3, divide that by 2, and we get 22.5 moles of H2. For part C, we are converting from one reactant to another. So we have 6.8 moles of hydrogen. How many moles of nitrogen do we need to cancel that out? So 6.8 moles of H2. We want the H2 to cancel, so we're going to have the 3 moles of H2 in the denominator and 1 mole of N2 in the numerator. So 6.8 divided by 3, 2.27 moles of N2. Those cancel out. So just again, to remind you, these numbers I'm pulling from the stoichiometric coefficients in the balanced chemical equation. This is the mole-to-mole conversion, and this type of thing is the heart of every single stoichiometric problem you could work. Let's see. This is another mole-to-mole conversion, and so I'm going to leave this one as an exercise for you to try. Here we have another mole-to-mole conversion. Again, I'm going to let you work this one as an exercise for yourselves. This one is a little silly, because you normally don't need to know how many molecules you're being produced. It's going to be a huge number, but let's go ahead and work it because it illustrates combining different types of conversion factors. And so here we are going to be going from moles of propane, that's the C3H8. We are going to convert that to moles of carbon dioxide. Okay, so that's the simple mole-to-mole conversion using the stoichiometric coefficients. And then we're going to go from moles to molecules of carbon dioxide. And that's a conversion factor that we've used previously, right? That one involves Avogadro's number. So let's work through this. 0.75 moles of propane. We want to convert that to moles of CO2. So we're going to have the 3 moles of CO2 in the top, and we'll have the 1 mole of propane in the denominator. And again, these come from the stoichiometric coefficients in the chemical reaction. So that takes us from here to there. Now we want to get to molecules using Avogadro's number. Avogadro's number for this problem, 6.022 times 10 to the 23 molecules per mole of CO2. Okay, so the moles of propane are going to cancel, the moles of CO2 are going to cancel, and we're going to be left with molecules. I'll put the number right there. And I'm getting 1.4 times 10 to the 24 molecules of CO2. And as we expected, that's a very large number. Okay, so a slightly different, slightly more complicated conversion strategy. This problem is identical to the one that we've just done in terms of its strategy. The numbers are a little different, but I will leave this as an exercise for you to try. Let's look at the next type of problem. Here we're starting to do the mass-to-mass conversions. So we have this hematite ore. It's reacting with carbon monoxide in a furnace to produce the iron metal, which is valuable, and then CO2 gas is the byproduct. And so we want to know how many grams of iron can we produce from a kilogram of this hematite iron ore. Okay, and so here is the strategy for this problem. We are going to go from the kilograms of the iron 3 oxide. We'll convert that to grams, and then we'll go to the moles of the iron 3 oxide. Then we'll convert that to moles of iron, and then the last step will be to grams of iron. So kilograms of the ore, that's what we're given. We'll convert that to grams. That's an SI to SI conversion. We'll use the molar mass of the iron ore to calculate the number of moles of the iron 3 oxide. Then we'll use the stoichiometric coefficients to convert from moles of the ore to moles of iron. And then we'll use the molar mass of the iron, the atomic mass of iron, to calculate the grams of iron that we can produce. So I'm just going to first calculate the molar mass of the iron 3 oxide. Okay, so we've got 55.85 for the iron, and there are 2 of those. And then it's 3 times 16 for the oxygens. I'm getting 159.7 grams per mole. And now we're ready to do the stoichiometric calculation. So I'm going to do the SI conversion in my head. So we have 1.00 times 10 to the 3 grams of the iron 3 oxide. We will divide by this molar mass to give us the number of moles of iron 3 oxide. So that takes us to here. Now we're going to use the stoichiometric coefficients, right? For every mole of the ore that reacts, we get 2 moles of iron. So I'm going to put 2 moles of iron in the numerator, and we'll divide by 1 mole of the iron 3 oxide. Finally, to get from moles of iron to grams of iron, we're going to multiply by the molar mass of iron. So that would be 55.85 grams per mole. So the grams of the iron 3 oxide cancel, the moles of the iron 3 oxide cancel, the moles of the iron cancel, and then we're left with grams of iron. So I'm getting from this calculation 699 grams of iron. Let's do another problem like that. This is bread and butter chemistry right here. And so you want to be pretty good at these types of calculations. Here we even have to come up with the reaction ourselves. And so where we have sodium reacting with water. So sodium metal reacting with water, and it produces aqueous sodium hydroxide and H2 gas. We want to make sure that this reaction is balanced before we continue. So sodium, sodium, balance, 1 oxygen, and we've got 2, 3 hydrogens. So we have 1 extra hydrogen on this side that we need to get rid of. We'll try the fraction trick here. Then we'll multiply the reaction by 2. So 2 sodiums, 2 waters, and 1 H2. That should be balanced. It is. And so we can think about our conversion strategy here. We're going to go from grams of hydrogen. We'll convert that to moles of hydrogen. And what they want is the grams of sodium. So we'll convert to moles of sodium and then to grams of sodium. Okay. We're going to need the molar mass of H2, which is 2.02 grams per mole. And we'll need the molar mass, the atomic mass of sodium, which will round to 23.0 grams per mole. So we'll take our 7.81 grams of hydrogen, and we will divide by the molar mass. Okay, so that's going to take us from grams to moles. Then we will use the stoichiometric coefficients to convert from moles of hydrogen to moles of sodium. So we want the sodium in the numerator and the hydrogen in the denominator so that it cancels out. And then finally, we'll multiply by the atomic mass of sodium. So our grams of hydrogen will cancel, the moles of hydrogen will cancel, the moles of sodium will cancel, and we'll be left with the grams of sodium. And I'm getting 178 grams of sodium from this calculation. Okay, so this is another illustration of the grams to gram conversion problems. Here we have another example of a gram to gram conversion. So I'm going to leave this one for you as an exercise. The next problem that we have here, it's one of these where you have to come up with the reaction. I'll go ahead and let you do that, practice your balancing. But again, this is going to be a grams to grams conversion. Well, I guess they want the final answer in kilograms. But it's more or less the same as the last two examples that we've done. Let's look for this problem here. This is the same thing, just a different reaction. And again, they want you to figure out what the reaction is and then balance it. So I'll let you practice your skills. And so we will stop this video right here, and we'll pick up next with some slightly more complicated problems involving limiting reactants in the next video.